Hi everyone, I'm Tracy Smith from Finding Physics. Today I want to talk to you about non-right triangle trigonometry. My last lesson I focused on right triangle trigonometry and its uses in the physics classroom. Today I want to look at problems that do not include right triangles. Again, that's why we're calling it non-right triangle trigonometry. As we go through this little mini lesson, I'm trying to give some of the basic skills to give you a foundation so you can start practicing non-right triangle trigonometry and you're more prepared to start your first physics class. So, let's talk about some of the basic terminology and information about a non-right triangle. A non-right triangle, first of all, is called an oblique triangle. This is a triangle that has no right angles in it. None of the angles are 90 degrees. So if we take a look at the triangle to the right, you can see that I have an angle right down here. That angle is obviously less than 90 degrees. I have an angle up here. This angle looks like it's greater than 90 degrees. And then there's the third angle over here, which also appears to be less than 90 degrees. We know, just like we said previously, that when you have a triangle, the three angles in the triangle are always going to add up to 180 degrees. So this is an important piece of information to know. Regardless if it's a right triangle or an oblique triangle, we still have the three angles adding up to 180 degrees. It's just when it's an oblique triangle, none of the angles in the triangle are a 90-degree angle. Now, this isn't a big deal, but what you have to realize is since it's not a right triangle, we can no longer use the sine, cosine, tangent functions, nor can we use the Pythagorean theorem. We can only use those if there is a right triangle. So the skill set that we talked about in the last mini lesson, all of those skills, at first glance at least, do not apply to an oblique triangle. So there's a new skill set. And what I'm going to talk a little bit about today is how we could use the law of sines and the law of cosines whenever we have a non-right triangle or an oblique triangle. So let's start. And let's take a look at the law of sines and the law of cosines. Now, there is something important for me to point out here. Whenever we're dealing with the law of sines and the law of cosines, it's more trig. I don't think that trigonometry and the algebra skills you need to use to solve these are that much more challenging than sine, cosine, tangent, and the Pythagorean theorem. They're just different. So, the other thing I want to mention is a lot of times you can get by without using these. But as you will see as we progress through this lesson today, it may be easier just to use your law of sines and your law of cosines when you're problem solving. So take a look at the triangle to the right first. What I want to show you here is how we label the angles and the sides so that you can tie it into the law of sines and the law of cosines. First, all angles are identified with variables that are capital letters. So we have in this triangle a capital A, B, and C, and those are our three angles. Now, we also have the sides labeled with A, B, and C, but they're lowercase, and it's set up a specific way. So if you look at where angle A is, across from angle A, that side of the triangle is lowercase a. Again, it has to be the side of the triangle that is across, not one of the sides that make up angle A. If you look at angle A is created by side B and side C. Okay, but over here at the bottom, we can see side A. And then if we go through our other angles and sides, here we have angle B, and across from angle B is side B. And then the same thing for C. If we take a look, we have angle C over here and side C across from that. So we have to make sure we have everything laid out properly on our triangle so that we can then use the law of sines and the law of cosines. So the law of sines. The law of sines is written out here, and you can see three proportionalities. It says the sine of A over side A equals the sine of angle B over side B equals the sine of angle C over side C. And whenever we're using these, typically we are setting two of these proportionalities together. So maybe we're looking at this section where we know three of the four pieces of information and we're solving for the missing piece. What does that mean? That means maybe you know angle A, angle B, and one of the sides, and you're looking for the other side. Or maybe you know the two sides and one of the angles, and you're looking for the other angle. So law of sines is very helpful based on what information you know. The law of cosines may also be used. I'm going to clear off all of the highlighting here just so we have a clear image to start with. So if I take a look at the law of cosines, a lot of times this is intimidating to people just because it's long. But if you notice, it looks a little bit like the Pythagorean theorem. It just has some extra information on at the end. And again, that's because this is not a right triangle. So if we take a look at the law of cosines, let's just use the first variation of the equation. If I was looking for side C, which is right here, I could use the law of cosines to solve for side C if I also knew side A, side B, and angle C. So if you take a look at this, if I know a side, angle, and a side, I could find the side across from it by using the law of cosines. I could also use the law of cosines if I knew the three sides of the triangle and I was looking for one of the angles. So law of sines, sometimes used, law of cosines, sometimes used. It all depends on what information do you know and which one of these laws is more appropriate to use based on what you know and what you're trying to solve for. And like anything else, folks, the more you practice, the better you get at using these. Now, what I'm going to spend more time talking about is what if you want to avoid using the law of sines and cosines. Sometimes this is something that some of you try to avoid. Other times, it's not that we're trying to avoid it, but I'm going to introduce a skill set that becomes handy as we go through a physics class. So take a look at this triangle here. This triangle, and I just made up random variables, folks. You may be like, where does she get L and M? I just picked two letters out of the alphabet. So let's say I had a value. Let me get my little highlighter here. Let's say I had a value, a number, for this side of the triangle. Instead of using a number, I'm just using the letter L as a placeholder, as a variable. And let's say I knew this other length of that side. I'm going to call that M for now. And I also know this angle in between them. And the purpose of this problem is to solve for this long side here. That's what I want to solve for. And I also want to figure out this angle that side is at. So that would be the purpose of the problem. Now, some of you may look at this and right off the bat say, hey, if I know a side, an angle, and a side, I could use the law of cosines to figure out this opposite side, which we're looking for, which is a true statement. You most certainly could use the law of cosines to solve for that. And then you could use the law of sines to solve for this angle down here. Perfectly fine, guys. That is an option. If you had this oblique triangle, you could indeed use the law of cosines to solve for that side value, and then use the law of sines to figure out that angle. Perfect use of those skills. But what I'm going to show you right now is a different way of looking at it. Here's the thing with physics class, folks. You do not always have to do things one way. And depending on how your mind processes things and how you see things, the idea is that as teachers, we should be giving you various skills so that you could attack the problem in a way that maybe it makes the most sense to you. So what I'm about to do now may seem more complex, but it does involve a skill set that we use a lot in physics class. So I want you to bear with me, entertain these thoughts, and then if you attend my workshop, we'll do more practice with it so you become more comfortable with the skills. Okay, what is this that I'm building up to here? I still want to solve for that long, right here, this long side of the triangle and the angle there. But what if I look at this triangle from a different perspective? If I look at this long line, what if I say that this long diagonal line could be the hypotenuse of a right triangle? Can you make a right triangle with that hypotenuse? I can. All right, so let me go over here and let's see what I can put together here, folks. A right triangle that would have that hypotenuse, I'll start down here. I apologize for my lines not even being that straight. Okay, so I'm trying to eyeball it so I can get a good right triangle here. Come on, you can do it. Okay, I know it's not perfect. I'm trying to draw it the best I can here. So what we have now is a right triangle that I just made. Like what, she just randomly makes a right triangle? Yes, I did. And what I did was I said, if I had that yellow diagonal line that I was looking for, couldn't I say that that could be a hypotenuse of a triangle that had one big long horizontal line and one big vertical line? Now you may think, why did you just make it a right triangle? Well, there's something I like about right triangles. I like that I can use sine, cosine, tangent, and the Pythagorean theorem with right triangles. Another thing I like about right triangles is that what I just did is I said this diagonal line that I'm searching for can be constructed from a horizontal line, which a lot of times I call the horizontal line an x component, because if we picture a grid, we have x and y in our grid. So I have an x component, or this horizontal line here, this guy here, my x component, and this big y component. And I like things being in x and y components because they're simple to kind of break down and combine, and I'll show you what I mean in a moment here. So if I could figure out what this big long horizontal line here is, this x component, and I could figure out this y component, I could use Pythagorean theorem to figure out what the hypotenuse is. And then I could also use my tangent function to get this angle here. However, it's going to take us a couple steps to figure out what those values are. So if I look at the x component, that horizontal line, I already know the length from here to here. I know this length. I have it designated with the capital letter L. I'm saying that's a known value. But what I don't know is the extra distance from here to there. That's an unknown right now. And I'm just going to call that unknown variable x. I need to figure out what that is, because if I want to know what the entire length is of this horizontal line, I would have to add together the L value plus the x value, and it will give me that total length, that total big x component. Okay, so that's one thing I need. So let's start there. Okay, how could I figure out this x piece? All right, folks, watch this. Do you see that diagonal line there? That I have it labeled M. I say that I know this number. It's some variable M. Do you see the right triangle that has M as the hypotenuse? Do you see it? Look at this little guy here. Here and there. So now I have another right triangle. I could use my right triangle trig skills to figure out what that bottom x component is. There's one thing though, I need to know what the angle in here is if I'm going to analyze that little green triangle. So then I stop and say, okay, let's look at what I know. Switch my colors here. I know that theta is the angle right in here inside this big triangle. We said we know that. We know that number in the problem, that theta value. I also know if I have a horizontal line, the angle going across that whole horizontal line is 180 degrees. Okay? So that means if this whole angle is 180 degrees and this little piece of it, well, it's not too little, it's a big piece, is theta, then the difference over here would have to be 180 degrees minus theta. Okay, so that's 180 minus theta. That's kind of a handful to write, but that's what I could do to express that angle that's right in here. I apologize for my poor penmanship here, folks. All right, so now if I look at my green triangle, I have an expression for this angle. I know the hypotenuse value is M, and I want to know what this bottom little x piece would be. Now, in my head, I can jump and say, I'm going to use the cosine function to figure that out. Why? Because I've been doing these problems longer than you've been alive. So it's second nature to me. But for you, that might not be the case. Completely okay. Here's the thought process that you should go through. You should say, okay, I am trying to find out this variable. This variable is adjacent to the angle that I'm going to know. Adjacent. Okay? I also know the hypotenuse. What trig function, right triangle trig function, has adjacent and hypotenuse? If you forget, you can write your SOHCAHTOA at the top of the screen, right? SOHCAHTOA. And you can say, oh, there it is, adjacent and hypotenuse. That's my cosine function. So what I'm going to do over here to the side is I'm going to say, I know the cosine of my angle. Now remember, my angle's a bit of a mouthful. My angle is 180 degrees minus theta. And again, this is going to be a number. You would have numbers for that. That's going to be equal to my adjacent value, which I'm calling the variable x, divided by my hypotenuse, which I'm saying is some variable m that I know. So if I want to solve for x, I want to get x by itself. I'm going to multiply both sides of this equation by capital M, and I end up with m times the cosine of 180 degrees minus theta equals x. And right there, I'm able to do a calculation. As long as I have numbers for m and theta, I could do a calculation and get a number for x. And then I could figure out what this whole leg is down here, because it's going to be my variable L that would be given in the problem plus x. That's what that entire length is. But I'm not done yet. Oh, yeah. That's only the horizontal piece of the right triangle. I also need the vertical piece. So how about we switch pen colors here, folks? I need to know that piece. I'm going to call that y. All right, so I need that y value too. If I'm making a big right triangle to figure out that big yellow diagonal line right here, then I don't just need this horizontal line, I also need the vertical line. So our next thought is, how do I get y? Well, I look and say, okay, I know this angle. Y is opposite that angle, and I know the hypotenuse. What trig function has opposite in hypotenuse? And I look up here, my SOHCAHTOA, opposite hypotenuse. That's my sine function. So then I can say the sine of my angle, which again, 180 degrees minus theta is the angle that I'm showing in that triangle, is equal to opposite, which I'm generically calling y, divided by the hypotenuse, which I've designated as m. So if I want to solve for the variable y, I multiply both sides of that equation by m to get the y by itself. And I end up with m times the sine of 180 minus theta equals y. So now I could calculate this out. If I had numbers for m and theta, I would have a value for y. And that would be this whole length here. I know it's starting to get a little bit messy and busy here, but hang in there with me, folks. Hang in there with me. Okay, so now my big right triangle, let's find it again. I have this big horizontal line, this big vertical line that makes a big right triangle with that hypotenuse. Now I could use Pythagorean theorem to solve for that big hypotenuse. Why? Because in the x direction, I know that value is going to be L plus x. I was given L. I solved for x up here. I sum them up. My other leg of my right triangle I called y, and I used this little triangle here to solve for that y component because it was its own mini right triangle. And over here, I did that, and I got an expression for y. So the last thing I need to do is use Pythagorean theorem to solve for that hypotenuse. I know it's getting messy here, folks, but I'm going to keep going. I could say with Pythagorean theorem, how about I'm going to call this big yellow diagonal line, I'm going to call it r. Why? Because I want to, and it's something that a variable I use a lot in physics class for the term resultant. But I'm going to use a capital R just as a placeholder. So when I write Pythagorean theorem, instead of saying a squared plus b squared equals c squared, I'm going to use the variables that I have in this problem. Okay, so you can kind of see I'm putting them in parentheses. So I would have my a, I'm going to call L plus x, and I'm going to square that whole thing. That's like my a squared. Plus my b is what I'm calling y here. So that's my b squared equals my c is going to be this r value because c is always your hypotenuse, r squared. And I'm not going to go through, all the steps. All I would have to do is take the square root of both sides to solve for r. I'm just kind of running out of space here. The last thing I want to say is if I want this angle down here, I could use my tangent function. And, where do I squeeze this in? Maybe I'll try to write it in here really small. I could say that the tangent of theta, I'm just calling this theta. Ooh, that's dangerous because I already have a theta over there. How about I call this theta 2? The tangent of theta 2, that means it's different than the other theta, folks. The subscript is making it unique. The tangent of theta 2, and I have to look at the big right triangle that I made because that's the only way I can use tangent is if I'm using the big right triangle. So tangent, according to my little cheater up here, my SOHCAHTOA, is opposite over adjacent. So tangent of theta 2 is my opposite leg, which is y, over my adjacent leg, which is L plus x. And then to solve for theta 2, you would have to take the inverse tangent of both sides. Now, if you're looking at this thinking, oh my goodness, what is going on? There is so much work here. It is a bit much. The screen's a bit overwhelming, but this is a skill set that we use a lot in physics class. The more you do it, the more second nature it becomes and the less intimidating. So please don't worry if this looks intimidating right now. You also may be saying to yourself, why in the world wouldn't I just use law of cosines and law of sines? Because that would have gotten me these values a lot quicker. Good thing to note, because sometimes you may want to use the law of cosines and law of sines instead of going through all these steps. I will also say that through part of my teaching, I require students to show me that they can do this skill. Even though I don't always make them use it when they're solving various problems, I do make them demonstrate that they understand the skill, because at some point it may be necessary to use it. When might that point be? Well, let's take a look at this. That's not a triangle. That doesn't have three sides. But could we use right triangle trigonometry to analyze something in this? So what is it that I would want you to analyze? Because I'm kind of making this up on the fly, right? What if I wanted you to solve for that side? Okay, I wanted that side. And let's say that you knew values for all the other sides. Meaning in the problem, you were given a value for that side, you were given a value for this one, you were given a value for that, and you were given some of the angles. Which angles, I'd have to go through and list them all. But look at what you can do here, folks. It's the big picture that I want you to see. The first thing we do in our head is we say, okay, I see that diagonal line. Could that be the hypotenuse of a right triangle? Sure. I can see two different ways I could draw it. One way I could draw it would be to say, about there. And again, your drawings don't have to be perfect as long as you use the right trig to do it. I know everything's not lined up great. So I see a right triangle there. Okay, that's one way I might look at it. Another way I could look at it is I could say it could be a right triangle going this way. Okay, that's another way I could look at it. There's not a right or wrong answer, guys. So that's very true. You could do a right triangle either way. And either way, you could use right triangle trig to help you solve for it. I'm just going to keep it this way for right now. And I'm going to try to show you something crazy on how we could solve all of this madness. So if I knew, pick a whole bunch of colors here. If I knew that value, I had a number for it, I could make a right triangle out of that too. I could say a right triangle that has that horizontal piece and that vertical piece, that makes a right triangle. So as long as I knew an angle in addition to the length of that side, I'd have to know, one of these angles in here somehow. And that all comes up in your problem. I could solve for these different x and y components using my right triangle trig. So let me call this, let's call this x1. And let's call this leg over here y1. So using my right triangle trig, I could solve for x1 and y1 as long as I knew that diagonal line and one of those two angles in that triangle. Again, it would have to be given some way that you would know that information. All right, well, I'm looking at this big yellow triangle and I'm trying to figure out the hypotenuse of the yellow triangle. And right now it seems like I'm not going anywhere. So let's take a look at another one of these diagonal lines. Again, we're looking at the big picture here, folks. Let's look at this diagonal line. Now, couldn't that diagonal line be a hypotenuse of a right triangle? Sure. I could make a right triangle with one leg this way and one leg going down. So as long as I knew that diagonal length, I had a number for it, and I knew one of the angles, maybe this angle over here, I could use that information to solve for this x piece, which I will call x2, just because it's the second triangle that I'm using here, and this vertical piece, which I'll call y2. So x2 and y2 are the green x and y legs, and x1 and y1 are the reddish one. Now notice there's an overlap with the red y1 and the green y2. Okay, I'll explain a little bit of that later. Now, that's not the only part. There is one more piece to this awkward shape that I drew here, and that is this piece right here. And that is just a vertical line. You will love horizontal and vertical lines and start to probably despise diagonal lines, but that's okay. We'll get used to it. So for this guy, I don't have to make a triangle. Why? Because it's not a diagonal line. It's just a vertical line. And since it's a vertical line, I'm going to call it Y3. Again, all horizontal lines I call X, all vertical lines I call Y. So what I'm trying to do is build pieces to make a horizontal and vertical yellow lines, which now it's hard to find the yellow lines. So if I take a look at this horizontal yellow line here, I made extra thick. I'll show it with a highlighter. I'm trying to find this length. If I look, that whole yellow horizontal line is the sum of x1 plus x2. I know they're not lined up, but can you see that this distance from here to here is the same as from there to there? Right? It's just not drawn right up against it. So my overall x value here that I'm trying to solve for, which I'm going to call it just big X, it would be equal to x1 plus x2. And that would be that big horizontal yellow line, would be that capital X. It would be the sum of x1 and x2. Now, if we take a look over here, let me get back to my yellow. I need this y value right here, this little piece. Now, how do we get that piece? Because there's a lot going on here. Well, I can see that I have y3, I have y2, and I have y1. So we'd have to combine these to figure out what we have for y3. So if we look, y1 is going down, y2 goes up, and then y3 is going kind of all the way up to the top. So if I want to know this overall y piece here, this gets a little tricky to write. My overall big y component, and that's the yellow part that I'm talking about there, is going to be y3, and then I'm going to have to subtract off this y1 value from y3. But then I have to kind of add up the y2 value. Okay. So I'm going to add up my y2 value. Let me make sure I put that all together. I have y3 minus y1 plus y2. And again, when we actually use numbers, this will be more apparent. That gives me the y part, capital Y of this yellow line. And over here we have capital X of the yellow line. And then, folks, we could use Pythagorean theorem to solve for that r, which I'm calling the resultant diagonal line there. That's a lot of work to solve for that piece. I'd also be asking in the problem for you to solve for the angle. So once we get to this point, folks, you would be using the Pythagorean theorem to solve for r by saying capital X squared plus capital Y squared equals capital R squared. Okay, and you could solve from r for that. And then I would want this angle here that I'm calling theta, and I could say the tangent of theta is equal to opposite over adjacent, which would be y over x, and that's capital Y and capital X. And you could use that to solve for theta. So all I'm trying to show you here, and again, I don't want it to be overwhelming, but I'm trying to show you how sometimes we take things that are not right triangles and we try to visualize it as right triangles so that we could use sine, cosine, tangent, and Pythagorean theorem to solve for pieces of it. So we can kind of take all the horizontal pieces together and make one big horizontal piece, and take the vertical pieces and make one vertical piece, and then make one overall right triangle that has a hypotenuse of what we're trying to solve for. So how does non-right triangle trig apply to physics? It ties back to that concept of vectors, and I know I haven't talked to you about vectors yet, but it will be coming, and it's going to be a lot. Everything we're talking about with these two trig lessons, they're the heart and soul of vectors. And so if you can get familiar and comfortable with right triangle trig and non-right triangle trig, when you get to vectors, and again, they're all throughout the school year, when you're dealing with vectors, it will be much easier. That's why we're practicing these skills now. The trig skills workshop that I'm going to be doing is going to be practicing these skills. So for the last lesson, right triangle trig, the workshop with that, we'd be doing a lot of right triangle practice. For this non-right triangle trig, we are going to take non-right triangles and other shapes and reimagine them as a combination of right triangles, so we could then use our right triangle trig to solve for whatever we need to solve for. Again, I know it may sound confusing at this point, folks. I apologize. I'm trying to kind of break it down into small pieces so that it's manageable for you as you progress through your physics class. So, you need more help, you want to look into more information, visit my website, findphysics.com. And there you could sign up for a tutoring session where we go over these skills one-on-one. You could look into the workshops that are offered that include these skills, or you could just search around for some more general tips and inspiration to help you with finding physics in your life. The goal is, folks, to show you how relatable physics is to everyone, and that you do have the power and the ability to break this down and use it to your advantage. I hope you have a great day, everyone. Bye.